Welcome back. Can we start again? Hello. My voice is audible? Sure. Now it is audible?
Yes, sir.
Yes, sir.
Somebody posted saying that voice is not audible. Now is it clear?
Yes, sir. Clear, sir.
Okay. Better than last time?
Yes, sir.
Okay. Okay. Just in case if you have any points to make, you please raise your hand or put it in chat box. Appropriately, I can do something from my end.
Okay, sir.
Okay. So now with this, we will continue from where we have left. Now, we did determine the value of evapotranspiration for a given situation, and I showed it in Excel. Now, similarly, let us look at another example, a slight variation to this, not much of a difference, but slight variation. In what way it varies, let me tell you. The problem statement is here. For an area in South India, latitude 12 degree north, the mean monthly temperatures are given. And here the statement is incomplete. Sorry for that. Maybe in class notes, I am not sure whether the same thing is present, but it should continue. The question is to decide the evapotranspiration taking the crop as rice with a crop coefficient of 1.1. So that correction I will make and appropriately send one more rejoinder in your WhatsApp group. You can please make a note of that. But here, what are the differences? See, the difference is nothing but the temperature again is given in Celsius, which needs to be converted into Fahrenheit. So that you can do with the relationship C by 5 is equal to F minus 32 by 9. In a similar way, you can change degree Celsius to degree Fahrenheit, the first thing which can be done. But whereas the 12 degree north, if it is provided in the form of a table where for latitude 10 and latitude 15, you have values, let us say. How to obtain the values for latitude 12? That is the question. So let me just take this as an example for discussion here. If daytime sunshine hours, 1 second, I write this here. If daytime sunshine hours, I will write this. Hours are provided for latitude 10 and latitude 15. If the place mentioned for you is latitude 12, how are you going to get the values for latitude 12? How are you going to get that? It is just on the basis of linear interpolation. Somebody is trying to rejoin. In case if you cannot rejoin, you disconnect and try to join again. I will admit there is some technical problem. If someone has lost the connection, let them rejoin again after one more try. Okay. So here, what we would do is the linear interpolation. You have latitude for 10, latitude 15. How to get for latitude 12, let us say. Now, what is the difference change in the value of sunshine hours? First, you have to look at. See, from 10 to 15, it is increasing. And for 5 degree change, 15 to 10, for 5 degree change, how much it has changed? It has changed by a value equal to 8.8 minus 8.6 per latitude means 15 minus 10. For every degree latitude, it changes by 0.04. Suppose if you want it for latitude 12, for latitude 10, you have 8.6. For latitude 10, you have 8.6. Then 12 is 2 degrees later. For every degree, it is 0.04. Therefore, for 2 degrees, it is 2 into 0.04. So you will get that value. You add these two. You get the value as 8.68 for latitude 12. Is this point clear to everyone? Linear interpolation, clear? Some response?
Yes.
Is it clear? Okay. Is it all right? If you cannot speak, you can put it in chat box. Is it clear?
Yes, sir.
Okay. If it is clear, we will move on. So that is what we have done here. See in chat box, somebody has. The point, not point 4, somebody is raising the objection. So I will try to show it here. See, for latitude 10, you have these values. For latitude 15, you have these values for daytime sunshine hours. But the place at which you need to compute or determine the evapotranspiration needs is at latitude 12. So because of which you need to obtain for latitude 12 through linear interpolation using latitude 10 values and latitude 15 values. Now, what is the difference between 10 and 15? It is 5, right? In latitude, how many degree difference? 5. Then what is the value difference between lat 5 and lat 10? It is 8.8 minus 8.6. 8.8 minus 8.6. For 5 degrees, it has changed by 0.2. For every degree, how much does it change? It is nothing but 0.2 divided by 5 degrees. That is 0.04. So for every degree, it changes by 0.04. So you keep adding 0.04 onwards to 10 to obtain 12. That means to say that 10 is 8.6. Latitude 11 is 8.6 plus 0.04. Latitude 12 is latitude 10, that is 8.6 plus 0.04 plus 0.4. Twice you have to add. So if you add it 5 times, you get again 8.8 at latitude 5. Is this point clear?
Yes, sir.
Okay, somebody raised in chat box, it is not 0.4, it is 0.04. You just check. 0.04, 0.2 divided by 5, not 0.04. So you just check that. Is this clear in chat? Not 0.4, but 0.04. Okay, good. So that is the only change here. So if you look into that, that is the only change. Rest of the thing will remain the same. The same values will be applicable. You will calculate the same value. In the problem statement, I have missed that crop coefficient of 1.1 for rice. So you just substitute that, and final value of evapotranspiration is written here, 103.04. So I will modify this little bit just in case if you have confusion. I can resend the updated notes to you. You can make use of this. Okay. So with this, we will end. Of course, there are a couple of other examples in between, maybe in the class notes also. This we have already discussed. As a part of evaporation topic, we have already discussed. No need to repeat that once again. We will continue for the next topic or next abstraction or the last abstraction in this particular module 2. So what is that we have? It is infiltration. The term infiltration literally indicates that it is the water which gets into, and it is the water which gets into the soil. And this infiltration is one of the very important abstractions of precipitation. A lot depends on our groundwater, on infiltration in respect of our groundwater storage, in respect of soil moisture, in respect of evapotranspiration needs of the plant. And here also, just like for the previous 2 abstractions, we will have a little bit of introduction, the factors which affect infiltration, infiltration capacity, and the measurement of this using double ring infiltrometer and an analytical procedure that is Horton's infiltration equation to determine infiltration or to understand this infiltration better would be attempted. And finally, the presentation of infiltration data through infiltration indices is another thing which we need to look at. So here, straight away, infiltration is the movement of water through the soil surface into the soil. It gets into the soil. This infiltration capacity of the soil at any time is at maximum rate at which water will enter the soil, and infiltration capacity depends on many factors. So the infiltration capacity of the soil at any time is the maximum rate at which water will enter the soil. This is how it is defined. And now you have to understand one thing. We discussed something called quantity of precipitation and intensity of precipitation. Quantity of precipitation is denoted in millimeters or inches or centimeters, whereas the intensity of precipitation is reported in millimeter per hour or centimeter per hour or inches per hour. Here also, you have to understand that infiltration capacity means what is the rate at which water is getting into the soil, so many millimeters per hour, or so many millimeters per minute, or so many millimeters per second. Based on that, we call it as infiltration capacity. So that you need to understand here. We will work out an example and try to understand things much better. So here, the various factors which influence infiltration capacity are the condition of the soil and the vegetative cover. So here, again, I go back to the type of soils like clay, silt, loam, gravel. When you compare gravelly soil or sand with clay, the porosity is much higher in a gravelly soil as compared to fine-grained clay soil. And because of which the movement of water in sand or in gravelly soil is much easier as compared to movement of water in clay. So because of this, the infiltration through rainfall into a gravelly soil or into a sand is much higher compared to what it happens for a fine-grained soil like clay. And there is another aspect to this. Getting in is easy for sand. Water getting in is easy in respect of sand, whereas it is difficult in respect of clay. And so as taking out is also something similar. See, it can easily get in, it can easily get out. That is a good property of an aquifer which constitutes gravelly soil or sand. Whereas clay is not that good an aquifer. It takes time for water to enter. It takes time for such kind of aquifer to give out water also. So that is the first thing what you need to know, how soil would influence infiltration. And similarly, the vegetative cover. If the top of the soil is covered with vegetation, say grass, in which case the flowing water gets arrested over an extended period, because of which infiltration rate would be better. Suppose if it is a barren land without any vegetative cover, in which case the moment the water hits the surface, it starts moving in the direction of the slope, and the time of detention of water is relatively less, because of which infiltration rate is also less. Hence, condition of the soil and the vegetative cover are the first and foremost parameters which will influence the rate of infiltration. Then, properties of the soil, this I have already said, whether sand or clay or silt or loam, depends on the porosity of the geology of the place, and hence, because of which sand takes it in abundant quantity, whereas the same thing is not possible in case of clay. Then the antecedent moisture condition. Suppose it has rained already the previous day or a week before. The soil is already moist, because of which not much water can get into the soil. Suppose it is the first rain of the season, then the soil is completely dry and the infiltration rate for such a situation is very quick. So these are the parameters which you can think of, which would influence infiltration or water of the rain getting into the soil. Then how are we going to measure this infiltration? So we are using infiltrometers. For evaporation, we use pans, class A pan. And for evapotranspiration, we use lysimeter. And here we use flooding type infiltrometer. So another type of the instrument which we make use of to measure infiltration. And the second method is measurement of subsistence of free water surface in a large basin or pond. Then rainfall simulators, some kind of computer-based arrangement where we can simulate such conditions. Of course, some assumptions are very much necessary. And the classical method of hydrograph analysis, which we look into in module 3. In module 3, we will discuss this hydrograph analysis in great detail. So coming back to flooding type infiltrometer, there are two types of infiltrometers: simple tube type. This is a tube type, and this is double ring infiltrometer, a ring within a ring. So there is one ring, and outside also there is one ring. Both are circular in cross section. One is of 30 centimeter dia, the other is double the dimension, 60 centimeter dia. And part of this infiltrometer is buried in the soil 15 centimeter below, just to simulate the conditions of the soil in which this infiltration has to be measured. The water which is added to the infiltrometer is being sent downward, shown by these dotted lines. So as in this simple U-tube, this is also buried in soil. See, major part of this is also buried in soil, right? The top is only 30 centimeter diameter. It is only one tube, whereas here we have two rings present. So this is the kind of arrangement what we have in simple tube type infiltrometer and double ring infiltrometer. So for better estimate of infiltration, double ring infiltrometer is ideal. Some explanation is given here. This is rings, a small spelling mistake here. Rings. A double ring infiltrometer is the most commonly used because of accuracy. The infiltration area is not represented properly by U-tube type, whereas here it is represented better. So because of which it is used. And it is a concentric two rings of 30 and 60 centimeter diameter. The other dimensions are very clearly shown here. No need to repeat that, but in any case, we can just make a mention of that. Water depth in both the rings are kept same during observation period. The measurement of water is done for the inner ring only. Inner ring, that is the inner 130 centimeter diameter ring only. The experiment is carried out till a constant infiltration rate is obtained. What do we mean by constant infiltration rate? See, in the beginning, water starts getting into the soil easily. Over a period of time, as and when the soil keeps on getting more and more moisture, the rate slowly, gradually reduces. At some point of time, the soil is totally saturated and no amount of water can get into that. So in which case, the infiltration into the soil will remain constant at certain level. And this would normally happen towards end of certain period after quenching the soil for some time. So that is known as constant rate of infiltration. So we will come to that when we discuss an example, we will come to that. So all these things will have relevance to this rain impact, disturbance of soil mass, border effect, limitation of the method. So all these things are there even with this case of double ring infiltrometer. Let us not worry about that. If we can get the data from this double ring infiltrometer, over a period of time, and that entire data can be used to usefully analyze and understand few things, which happens by using Horton's equation. So Horton's equation, it takes all that data what we collect for infiltration through this double ring infiltrometer or simple tube type infiltrometer, and finally we arrive at an equation which can provide us the estimate of infiltration rate at any point of time. So this is something what we need to look at in great detail. So how are we going to define this Horton's equation? This is Horton's equation. So you look at this. This is the Horton's equation which we need to use. And here, the definition of the term, Fp represents infiltration capacity at any point of time t since the start of the rainfall. At any time, whatever the infiltration capacity is, that we call as Fp. And Fc, C stands for constant, final steady state infiltration capacity. Fc, final steady state infiltration capacity. Here, it would become constant because it would have saturated the soil to a great extent, right? So this is another thing what you need to remember. And then F naught, infiltration capacity of the soil in the beginning. F naught, the original, the beginning time. Fp at any point of time. Sorry. Then Fc is the constant rate of infiltration. And then we have the term Kh and T. Kh is known as, K suffix H is known as Horton's decay coefficient. T stands for the time at which we are measuring. And Tc is time at which the value of this infiltration becomes constant. It ranges from 0 to any time t up to Tc. So we start from time t equal to 0, we end with time t equal to Tc. This is the range of time. So at time Tc, the value of the infiltration will be Fc, that is steady. It is a steady state infiltration or constant rate of infiltration. So this is another thing what you can remember for this situation. So moving on, I have said this already. Then cumulative infiltration capacity is nothing but the integration of this. We will come to that over a period of time. We add all of that. Integration is nothing but successive addition. We will come to that. Now let us look into a simple example which illustrates few things, basic things for us. Later we will look into other parts of this, how to use Horton's equation for our purpose. So look here, infiltration capacity data obtained in a flooding type infiltrometer test is given below. See here, time since start in minutes, time t, cumulative infiltration depth, uppercase Fp. You don't get confused with lowercase values here. They stand for different. And here, this is Fp uppercase. So using this, how to get Fp, infiltration rate at any point of time. So I will show you how it is being done. So this is very important. First, we have to understand this. 1 second. The data as obtained from, this is the data as obtained from double ring infiltrometer, let us say. So the time in seconds, what you have, time in minutes, time in minutes you have, the cumulative infiltration depth you have. Then what is that which has gone into the soil in fixed intervals of time, you have to calculate, because this represents only cumulative value. Between time 0 to 5 minutes, in 5 minutes duration, 1.75 centimeter has gone inside. Similarly, between intervals 5 minutes since to 10 minutes since, that is again in 5 minutes duration, it has gone into soil by an amount equal to 3 minus 1.75. Is this point clear? That is infiltration depth, or I will just write depth. We may be running out of time in 10 minutes, till then we will continue. See, the depth between 0 to 5 minutes is equal to 1.75 minus 0. So this is what it has gone inside. And similarly, for the next 5 minutes, it is equal to 3 minus 1.75. For the next minute, it is 3.95 minus 3. Is this clear? And similarly, for other 5 minutes interval, how much has gone inside? What is the depth by which it has gone inside can be determined. And each of that has happened in 5 minutes time or 10 minutes time, whatever, you just check. From here to here, it is 5 minutes. 10 to 5, it is again 5 minutes. This is duration. Let me just write duration, 5 minutes. Then 15 to 10, 5 minutes. 25 to 15, 10 minutes. You look at this. 45 to 25, 20 minutes. Then 60 to 45, 15 minutes. 75 to 60, 15 minutes. 90 to 75, 15 minutes. 110 to 90 minutes, 20 minutes. 130 to 110, 20 minutes. So the duration in which so much of depth has gone into that. Therefore, what is intensity? Intensity is expressed as centimeter per hour, let us say. We are expressing it as centimeter per hour. So in 5 minutes, it has gone by 1.75. Therefore, in 1 hour means in 60 minutes, it will go by 60 divided by this 5. 1 second. Equal to 60 divided by 5 star 1.75. So this is the intensity, 21 centimeter per hour. Similarly, you will calculate for the next cases also, looking into individual depth and duration, those values would come like this. 21, 15 centimeter per hour, 9.3 centimeter per hour. If you look into these values, the intensity has varied. Whereas towards the end, the intensity has remained more or less the same. This can be considered as constant or steady state of infiltration FC. And this 21 represents, or rather the 0 represents F0. You can take this as F0, or sometimes you can take this also as F0, depending on the analysis you do. And all other values in between will be taken as FP, the value of infiltration at any given point of time. These are the values I have indicated in your class notes. You can look at this. So all of that here, if you look into this, these are the values I have indicated. Do you have any doubt in understanding this determination of infiltration rate? Any doubt? Please let me know. Any doubt with this? Some response necessary. Anything? Nobody is speaking. Is this clear or not? Please make use of chat packs at least.
Yes, sir. Clear, sir.
Okay.
Clear, sir.
Clear, is it? Okay. Then using this, how are we going to plot time t and infiltration rate? See here, we have to plot few graphs, just as we represented data in the first module. Here also, for abstractions of precipitation, the presentation of the data is very important. So in this respect, the problem statement desires a plot of time t against infiltration capacity. Time t against infiltration capacity, FP. So this plot has to happen. How are we going to do that to begin with? So let me just time t as a function of time t. This is your time t. This is your intensity. This is time in minutes. This is your intensity. Suppose if you wish to plot this, how are you going to do this? So let me just show you how this can be plotted. In exam, you may have to use graph sheet for the purpose. So here, let me just show it to you. Time t. 1 second. From 0. Then the intensity here. So go to this charter, scatter graph. Look here. The graph looks like this, where you can represent few things. 1 second. Chart title has to be given. Axis title also. The axis title, primary horizontal, is time in minutes. First thing. Then primary vertical, infiltration capacity in centimeter per hour. That is the vertical axis. And the chart title here, time versus infiltration rate FP. You can show this way. Now, sometimes it may be necessary for us to get an equation for this in order to determine at any point of time or to extrapolate or interpolate values. A best curve fit is an easy option in such situation. Suppose if you wish to provide, may not be from examination point of view, just professionally speaking as an hydrologist, if you wish to do this, you may wish to add a trend line here. If you add a trend line, straight line will not match. And similarly, if you think of polynomial, 2 degree, it will not match. 3rd degree, it matches approximately. Or suppose if you are thinking a power series, look here, it perfectly matches a power series, exponential one. The Horton's equation, what we are talking, has got an exponential decay term just because it becomes a best fit for the purpose. Now, if you look into this and show the equation on the sketch here, so look here, an exponential equation is obtained. So I will make it a little bigger such that you will see it better. Sorry. Look here, 60.179 x to the power minus 0.621, an exponential relationship where y represents the infiltration capacity, so many centimeter per hour, where x represents time since the commencement of the rhyme. You substitute any value of the time here, and whatever value which corresponds to that as infiltration capacity is obtained from this equation. Is this point clear to everyone? Any doubt with this diagram in this graph? Any questions? This is the basic thing from which we would start. So we have just under a minute to go. With this, probably we may have to conclude. Next class, what we will do is that we will take it further. I want each one of you, again, I insist that you practice all these things on a graph sheet. Unless you practice all these things on a graph sheet,